Welcome to the fastest way to learn data structures and algorithms. Today, we are mastering a top-tier system design favorite, LeetCode 295, find median from datastream. This problem is the gold standard for understanding heaps and real-time data processing. If you want to ace your next big tech interview, you need to master this pattern. The challenge is to design a data structure that supports two operations. First, add number, where we receive an integer from a continuous stream. And second, find median, which returns the middle value of all numbers seen so far. If the total count is odd, the median is the middle element. If it is even, it is the average of the two middle elements. The catch? We need to do this efficiently as the stream grows to millions of numbers. Think of a balancing scale with two trays. On the left tray, we keep the smaller half of our weights, and on the right tray, we keep the larger half. To find the median, we only need to look at the heaviest item in the small tray, and the lightest item in the large tray. As long as we keep the trays balanced in size, the median is always right there at the top of the trays. To implement our balancing scale, we use two heaps. A Max-Heap for the smaller half, and a Min-Heap for the larger half. When a new number arrives, we first push it into the Max-Heap. Then, to keep things sorted, we take the largest element from the Max-Heap and move it to the Min-Heap. Finally, if the Min-Heap becomes larger than the Max-Heap, we move one element back. This handoff strategy ensures the Max-Heap always contains the smaller numbers, the Min-Heap contains the larger ones, and they are always perfectly balanced. Look at the screen. We start with two empty heaps. Our data stream is 1, 2, and 3. First, we add 1. We push it to the Max-Heap, then move it to the Min-Heap. Since the Min-Heap is now larger, we move 1 back to the Max-Heap. Our median is simply the top of the Max-Heap, which is 1. Next, we add 2. We push it to the Max-Heap, then move the largest element, which is 2, over to the Min-Heap. Now both heaps have one element. The median is the average of the tops, 1 and 2, giving us 1.5. Finally, we add 3. We push it to the Max-Heap, then move the top, 3, to the Min-Heap. Now the Min-Heap has two elements, so we move its smallest, 2, back to the Max-Heap. The Max-Heap is now larger, so its top, 2, is our median. In our Python code, we use the heap queue library. Note that Python's heap queue is a Min-Heap, so to simulate a Max-Heap, we store our numbers as negative values. In add number, we push the negative number into small, then pop it and push the positive result into large. If large grows bigger than small, we move the top of large back to small. In find median, if small has more elements, we return its top value, remembering to negate it back. If they are equal, we take the average of both tops. This gives us O of log n for adding, and O of 1 for finding the median. For time complexity, adding a number takes O of log n because we perform heap insertions and deletions. Finding the median is a lightning-fast O of 1, as we only look at the heap roots. For space complexity, we store all n numbers, so it is O of n. And that is how you balance a data stream like a pro. If this two-heap trick clicked for you, hit that like button and subscribe to Leo Academy for more premium DSA guides. See you in the next one.